LLM systems fail quietly under load. Queues grow, latency explodes, and costs rise. Admission control fixes that at the front door. This is the workflow you'll know how to run when we're done, which scores incoming requests and admits high-priority ones while shedding to protect tail latency. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Admission control sits between clients and models. It decides who gets in now, who waits, and who gets politely refused. Systems use it when bursts would otherwise blow up P95 latency or budget. Success looks like steady response times, predictable cost, and fewer angry downstream services. We reach for it when models are hot, token bills climb, or some tenants keep pushing heavy work. Intuitively, admission control scores requests by value and cost. It knows current load and available headroom. It can carve quotas for fairness, defer cheap work, or drop obviously expensive tasks. Think of it as a bouncer with a scoring rule, a capacity meter, and a set of club rules that enforce fairness and protect the dance floor. We will build a small Python admission controller. It will show a priority scorer, a capacity limiter, per-tier quotas, defer and drop rules, and a tail-aware guard that predicts queuing impact. None of this is magic. Each step is a simple function and a short loop. Now we'll implement the scorer. This snippet computes a simple priority score that prefers urgent and low-cost LLM requests. The list named Rex holds 3 requests with a tier, a kind, and an estimated token count. The function score combines a tier-based base value, a small boost for chat requests, and a penalty that grows with tokens to approximate cost. The best variable selects the highest scoring request using max with the score function as its key. Increasing tokens lowers the score, while higher tiers improve it. Switching kind to embed removes the chat boost. The printed result shows which request would be handled first and its computed priority. Next, we limit intake by current capacity, so the system never exceeds a safe queue size. This example applies capacity-aware admission to keep the queue from overfilling. The variables max queue and queue depth define the limit and current load, and headroom is the safe number of additional requests. The call heapq.nLargest selects the highest scoring requests up to headroom using the score function from step 1. The list IDs captures the resulting admitted identifiers for logging or metrics. Raising max queue or lowering queue depth increases headroom and admits more work. Doing the reverse constrains inflow earlier. The printed result confirms which requests were allowed in and the exact admission budget used. Now we add fairness, so one tier cannot dominate the budget. This code adds weighted fairness, so one class cannot crowd out others. The dictionary weights encodes a target share for each tier, and groups partitions recs into per-tier lists. The quotas dictionary converts weights into per-tier admission counts from headroom, guaranteeing at least one slot where possible. For each group, heapq.nLargest picks the best scoring candidates within that bucket using the score function. Then the code merges them into pick. The final IDs list is sorted only for stable reporting. Increasing a weight shifts more budget to that tier, while decreasing it returns capacity to others. The printed result shows per bucket selection and an example quota. Next, we need a simple policy to defer or drop under pressure, rather than admit everything. This snippet issues defer and drop decisions to protect capacity under load. The variables max queue and queue depth model a busy moment, producing headroom of one slot. The function plan returns an action for each request. Drop if the token count exceeds a hard cap. Defer if the request is free tier and space is scarce. Otherwise, admit. The retry after value RA scales with congestion, using queue depth relative to max queue to set a short, fair delay. The acts list collects outcomes, and DS filters defer times to summarize the minimum backoff to tell clients. The printed result shows how many were deferred and the earliest retry window. Finally, we guard tail latency by predicting service cost before admitting. This code protects tail latency by predicting service cost before admitting. The function svcms estimates per request service time from kind and tokens. The variable target sets a P95 style budget in milliseconds, and tail estimates queuing delay from the current queue depth and the average service time of recs. Candidates are sorted by the score function, and the loop adds only those whose tail plus own service fits under target, capped by headroom. Increasing target admits more during bursts. Decreasing it sheds more to hold latency low. The printed result confirms which requests are safe to run now and the current tail estimate. Mapped to a real deployment, the scorer becomes a lightweight service in the request router. Metrics from admission decisions feed dashboards and alerts. Clients receive clear retry after headers for deferred work. The same patterns work for multi-tenant APIs, internal pipelines, or a serverless front door that must keep latency predictable while usage spikes. Recap: admission control scores requests, enforces capacity, and protects tail latency. Use it when you must keep P95 stable or control cost under bursty load. Caveat: simple heuristics can bias against some workloads, so monitor fairness and adjust weights. Next step: tune the target P95 style budget in the tail guard and measure how admitted volume and P95 latency trade off. If practical AI engineering helps, subscribe and watch the AI engineering videos.